Hello, everyone. So we're going to pick up where we left off talking about the photon gas. If you recall, we worried about we treated each mode, which I was labeling with a little r here, as an individual quantum harmonic oscillator, and we found the average occupation number of those oscillators, the average number of photons basically in each mode, given by this expression over here. And we counted up the modes by actually doing our mode counting argument again, thinking about plane waves in a box, and we found that the number of modes of frequency omega, and we've included a factor of 2 here for polarization, since you can have 2 different transverse polarizations for each spatial mode, is given by volume over pi squared c cubed omega squared d omega. And before, when we talked just about the individual modes, we said the partition function for all the photons was going to be the product over all those modes of the individual partition functions, which we have here. So we can find the free energy is just going to be minus the Helmholtz free energy, that is. It's going to be minus kT natural log of the partition function for the photons, right? And ordinarily, so the natural log would turn this product into a sum, but we're already going to turn that sum into an integral over frequencies since we have a density of states. So what we're going to end up here is we're going to have a kT out front, right? We're going to have a volume over pi squared c cubed, which we had before. Then we're going to have, we've gotten rid of the minus sign because we're going to take this piece that was in the denominator and we're going to just do the log of that. So that's going to eat the minus sign. We're going to have integral of 0 to infinity of omega squared d omega from our density of states. And then we've got natural log of 1 minus e to the minus beta h bar omega. All right, so that all makes sense. Turns out if we change variables, we do our usual variable change where we define x to be beta h bar omega. If we do that, we then have that the free energy is given by, we keep a bunch of factors out front here. We have the volume, and then we're going to have k Boltzmann T all to the 4, and we're going to have pi squared, c cubed, and then we're going to have an h bar cubed down here. Right? And then the integral is just going to be the integral over x, our dimensionless variable, and that's still going to run from 0 to infinity, but that's going to end up being x squared natural log 1 minus e to the minus x dx, okay? And it turns out you can actually integrate this thing by parts, and if you do the integral, you end up with, of course, as you might imagine, as you always do, minus pi squared over 45, because that's the most natural thing in the world. So, rewriting that for 1 second here, we have the free energy Okay, so I rewrote what I had before. I realized I'd made a slight mistake with the pi's, so this is the correct expression for the free energy. And if you know the free energy, then you can find the Helmholtz free energy, then you can find the pressure, right? The pressure is defined as minus partial free energy, partial volume at constant temperature, right? And in this case, when we talk about particle number, we have to be a little careful what we mean by particles. Here, I guess that would be equivalent to saying constant mode number, because we're not messing with the number of modes at all. All right, so if I actually look at this and I take the derivative, taking the derivative with respect to volume is trivial, right? And we end up with pi squared k Boltzmann T all to the 4 in the numerator. And then we have 45 h bar c all cubed in the denominator. And that, if you recall from what we had before from last class, that's actually 1/3 the total energy density is the pressure. Now you can actually get that from classical electricity and magnetism. If you really worry about either electromagnetic waves or if you worry about photons bouncing around in a box, you can actually work out that the pressure ends up being 1/3 the energy density. Now we can do a little bit of thermodynamics. If we know the free energy and we know the pressure and we know the energy, we can actually back out and find the entropy, right? There's different ways we can do that. I will cut to the chase and tell you that the entropy of the Fermi gas ends up being 4/3 hang on. Okay, 4/3 A T cubed times the volume, where A is defined as pi squared over 15 h bar c all cubed. And I'm 99% sure I've got those constants correct. Okay, so what we can see is that the entropy is nice and extensive and depends on the volume, exactly as you'd expect, and it depends on T cubed. And again, we could have gotten this, for example, from F equals E minus TS, right? Okay, so knowing these things, we know the entropy, we know the free energy, the Helmholtz free energy. I just want to point out, if we wanted to, we could actually do a tiny bit more thermodynamics. We could actually find the Gibbs free energy, right? Definitionally, that's the Helmholtz free energy plus PV. And if you plug everything in, you end up finding for the photon gas, the Gibbs free energy is actually identically 0. What on earth does that mean? Well, remember, the Gibbs free energy is also the chemical potential times the number of particles. The number of particles in this case, if we think of the number of particles as photons, or even as modes, doesn't matter, it's clearly non-zero. The fact that the Gibbs free energy is 0 tells you that the chemical potential for this system, for the photon gas, must be 0, right? The reason the chemical potential is 0 is because photon number is not conserved. We mentioned this last time. If you think about it, if we think about our definition of chemical potential as the amount of energy it takes to increase the particle number, the excitation number, by 1, what you find is that since photons can have sort of arbitrarily low energy, including 0, then at least in the limit that your cavity is large, then your chemical potential in fact does go to 0. All right. Now, what else can I tell you about blackbody radiation? Right. So we've seen the expression for the spectral density for the blackbody radiation, and we saw what it does. We saw the Wien's displacement law, which says that the peak frequency moves linearly with temperature off to higher frequencies as the temperature goes up. We saw the Stefan-Boltzmann relation, which says that the radiated power, the radiated intensity, is going to go like the Stefan-Boltzmann constant times t to the 4. What else can we learn about blackbody radiation? Well, one of these things you probably already know all of these things. One major point, though, is the universe is a really good blackbody. Now, let me tell you a little bit of the history behind this, right? So take yourself back to 1964. Bob Dickey is a theorist at Princeton, and he is a cosmologist. He's worrying about the beginning of the early universe, and he had this idea that the universe must have, because the universe is expanding, the universe must have at one time have been a lot denser and a lot hotter than it is now. And he thought very hard about this and realized, hey, if you look out in space, you can probably see the residual glow from back when the universe was really hot. He was trying to scare up experimentalists to look at this problem. And when he was going around talking to different people at different universities, trying to get them interested in doing this, he heard a story. He heard about how Arno Penzias and Bob Wilson, who, by the way, was a Rice undergraduate alumnus, they were at Bell Labs in Holmdel, New Jersey, and they were working on trying to actually well, they were getting started on radio astronomy, but one of the things they were also doing, the reason Bell Labs was paying them to do this stuff is because they were worrying about transmitting microwave signals to and from satellites in space. And they had built this giant horn antenna, and they were detecting a mysterious background hiss whenever they pointed this thing at the sky. And they spent a long time convincing themselves that it was real and not just the fact that like there were pigeons nesting in their antenna that were leaving pigeon droppings everywhere and so on. But in the end, Dickey was sort of depressed to find out that he'd been beaten to the punch, that he'd been scooped, because Penzias and Wilson had in fact detected what we now call the cosmic microwave background. Background. All right. This has now been measured in excruciating detail. It was measured in the early 90s by COBE, the Cosmic Background Explorer, and in the 2000s by something called WMAP, the Wilkinson Microwave Anisotropy Probe. And let me show you just how good a black body the universe really is. What you're seeing here is a plot of the cosmic microwave background spectrum as a function of frequency. The frequency happens to be given in inverse centimeters or wave numbers. And then this is the intensity in kind of a funky radio astronomy unit. But the point is that the green line is a theory fit, and the red crosses include the error bars, and those are the Cosmic Background Explorer data from the early 90s. And what you find is that the temperature is, to very good precision, 2.71 Kelvin. So the universe is filled with microwaves. These microwaves are distributed in terms of spectral intensity versus frequency like a black body, an incredibly accurate black body. And the temperature is 2.71 Kelvin. So where on earth did this come from? The idea is that in the early universe, in the really early universe, the universe was filled with a plasma, right? I mean, we're not going back terribly far, but we're going back to maybe a couple 100,000 years after the Big Bang. The universe is filled with plasma. It's got electrons and protons bopping around, and maybe a few alpha particles and a few deuterium nuclei and so on and so forth, right? But once, so the universe is busy expanding, so you've got a box with a bunch of photons in it, and it's expanding. And once basically T universe falls below around 11,000 Kelvin, which by coincidence is, or not coincidence, is around, energetically speaking, 13.6 eV. You recognize that as the Rydberg. At some point then, the electrons and the protons decide to form hydrogen atoms, and they're no longer ionized. And now that they're no longer ionized, their ability to absorb the radiation changes dramatically, and the radiation basically, the photons basically decouple from the matter to some large degree. And now, as time goes on, the universe continues to expand. T photon just acts like you've got a photon gas in a box, and you're expanding the box. The existence of the microwave background and the fact that it's basically everywhere you look in the sky is actually remarkable evidence for the expansion of the universe. Now, there are a couple of big questions that come up. Question one, let me back up. How do different parts of the universe know to be at the same temperature? To put that another way, if you look, say, along galactic north, you can see out to around 13 billion light years away, And if you look down to galactic south, you can see about 13 billion light years away. The universe simply has not existed long enough for those two parts of the universe to be causally connected to each other. So how do those two parts of the universe end up at the same temperature? How were they talking to each other early enough in the universe to end up early enough in the history of the universe to end up at the same temperature early on, so that when the universe expanded, they were able to end up at basically the same temperature now in this epoch? The answer seems to be something called inflation. You may have heard of inflationary cosmology. This is the idea that the universe itself expanded at some large hyperlight velocity early in its existence. Space-time itself expanded. And so the idea was that once upon a time those areas were causally connected, but they're not causally connected anymore. Now, there's all kinds of issues with inflationary cosmology. Just this week, I read a very inflammatory blog post by a very smart writer pointing out, calling into question whether inflationary cosmology is really a proper scientific theory. But anyway, if you want to read more about this is the term you should look up. Now, the second question that comes to mind, and then we'll get back to doing some statistical mechanics pretty soon here. The second question that comes to mind is, how uniform is the black body? That is, if I look to different parts of the sky, do I always get exactly the same temperature? Is everything completely isotropic? And the answer is no. Everything is not perfectly isotropic. There are small anisotropies in the microwave background. And those anisotropies are, in fact, the things that were being measured by WMAP, the Wilkinson Microwave Anisotropy Probe. And the anisotropies on different angular scales, so they're broken down in terms of spherical harmonics, your favorite thing, I'm sure, after all the various classes you've had. And you could talk about a dipolar component and a quadrupolar component and an octopole component and so on and so forth, of little variations in the microwave background. And by looking at how those things are distributed statistically across the sky, it's provided an incredibly exacting test of some of the ideas of inflationary cosmology. And it's actually some of the evidence that tells us that the universe is, say, 5% regular matter, 20% dark matter, and 75% dark energy, whatever the heck that is. Okay, so one more interesting digression beyond vanilla statistical mechanics before we get back to talking about the quantum gases. All right. Remember when we first started writing down the energies of our different electromagnetic modes, and we said, oh, we're just going to treat them like quantum oscillators, but we're going to throw away the 1/2 h bar omega. Well, you remember the 1/2 h bar omega? What happens if we include that? Because we have no reason to really throw it away beyond just saying that we'd like to. The point is, and I mentioned this in class before, general relativity says there is an absolute zero of energy density. That's what happens when space-time is flat, right? You end up with flat. Okay. So how bad is the problem then of neglecting the 1/2 h bar omega? Because remember, quantum mechanics tells us we don't really care what the zero of energy is, particularly if there's always a constant background there. We can just measure energy differences and we don't necessarily care. Well, let's figure out how bad it is. The energy density as a function of frequency, right? Using our density of states, it's going to be basically 1/2 h bar omega times our density of states. And that's going to end up being h bar omega cubed d omega all over pi squared c cubed. And if I integrate that over all frequencies, obviously it blows up, right? So this is the return of the UV catastrophe in some sense. Remember, where did this h bar omega, 1/2 h bar omega come from? The idea is that every one of our electromagnetic modes has should have a 1/2 h bar omega 0-point electromagnetic energy in there. All right. So you should ask yourselves a couple of questions. So, like, is there really 0-point electromagnetic energy? And the answer is, unfortunately, yes. We know this from quantum electrodynamics, it turns out, and in fact, the Lamb shift, when we calculate the Lamb shift, which is that, the fine structure splitting in hydrogen, if you actually want to calculate that from first principles, that's often interpreted as proof that there really is 0-point electromagnetic field. Okay. Can we throw in a cutoff frequency? Right? That was one way of trying, in the Debye problem, the way we avoided everything completely blowing up, was we basically said, oh, there's a Debye frequency that's the highest frequency we're allowed to have. So can we throw in a cutoff frequency here and save ourselves? You could. So you could try what's the so-called Planck energy scale. So you can basically take h bar, the speed of light, and the Newtonian gravitational constant, big G, and you can combine them to get something with units of frequency. And you can say the idea here is we may not have the theory of quantum gravity, but we know if we go up to frequencies that high, we'd have to worry about quantum gravity effects. So maybe that's a convenient cutoff. If you do that, you end up finding out that U total, so if you integrate this up to the cutoff frequency, the energy density ends up being something like 10 to the 113 joules per cubic meter. And yes, that should bother you, right? Because observationally, what is the energy density of apparently empty space? We can get that pretty well by deciding how flat space-time looks. So observationally, it turns out that U total seems to be something like 10 to the minus 9 joules per cubic meter or less, right? You need to, the slightly apparent slight acceleration to the expansion of the universe suggests that there is a slightly non-zero value of this number. If anything, it's slightly negative, which is interesting. But the point is that basically these two things differ by 122 orders of magnitude. So this right here is, very explicitly the problem between quantum mechanics and general relativity. Statistical, basic statistical mechanics plus the 0-point energy here tells you that the energy density from electricity and magnetism should be, in space-time from the 0-point energy, should be extremely large. We know that 0-point energy is real and it exists because it has testable consequences like the Lamb shift. Yet observationally, there's nothing there, or very, very little there. How do we get out of this dilemma? No one knows. If you figure this out, you can go and get yourself a Nobel Prize. One possibility is that there is something called supersymmetry. I'm certainly not an expert on supersymmetry. There are a couple of people in the department, Mustafa Amin, Matt Foster, could talk intelligently about what we mean by supersymmetric variables on the mathematical level. But one of the ideas is in the world of supersymmetry, the idea is that fundamentally there should be a symmetry between all the fermions in the universe and all the bosons in the universe. And there ought to be partners for every one of these particles. Now, if supersymmetry was perfectly preserved, then all of the superpartners and all of the normal particles would have the same masses. They don't. So clearly supersymmetry is broken in some way. But the idea is the following. For every photon, or rather for the photon field, there is a photino. What is the photino? So the photon is a boson, right? The photino would be a fermion that would otherwise be in many ways like the photon. And the deal with the superpartners, the fermionic superpartners, they have, I should say the fermionic ones, they have minus 1/2 h bar omega 0-point energy. That sounds very cheesy, but it's true. So the idea is that for every frequency mode, you get the 1/2 h bar omega worth of 0-point energy from the electromagnetic field. You get the minus 1/2 h bar omega 0-point energy from the photino, from the superpartner of that thing. And guess what? These things almost perfectly cancel. And so this saves the day. I have to say, this is not, by the way, this is not the only motivation or even the primary motivation for supersymmetry. Personally, I do find it one of the few compelling arguments in favor of supersymmetry, given that there is so far is absolutely zero experimental evidence in terms of direct observation of particles for any of the superpartners. So as far as we know, observationally, there aren't any photinos, there aren't any selectrons, there aren't any squarks. But there might be out at some very exotic high energies or in some system where we can't actually detect them readily. So to wrap up talking about the black bodies, then I think you now know what have we learned here? Right? We've learned the energy density, free energy, pressure, entropy of the photon gas, what we're calling the photon gas. We've learned the black body spectrum. We've learned that the Stefan-Boltzmann relation, and we've learned that we can actually calculate the Stefan-Boltzmann constant from first principles. All right, so let's stop there for a second, and we're going to pick back up in a minute talking about the quantum gases in general. All right, so now we're going to talk about the quantum gases. What do I mean by the quantum gases? Well, the point is, in our classical ideal gas treatment, we never really worried about the restrictions on occupying single particle microstates. I've talked about this before, but what we did was we found the partition function for a single particle, and we worried about distinguishability by writing something like Zn. The partition function for a zillion particles was 1 over n factorial z of one particle all to the n, right? That ignored interactions between the particles. So this was non-interacting, pardon my handwriting. And we didn't really worry about anything to do with double occupancy of states or statistics of what, when you exchange particles, what has to happen. All right. So now in quantum systems, if basically N3D approaches the quantum concentration that we had from before, you have to worry about this stuff. You have to worry about statistics, right? Your density in phase space is high enough now that you're really talking about putting particles into states that might already be occupied. So what are your choices? What are the things you have to consider? Well, one possibility, of course, are bosons. And when you took quantum, you learned what bosons are. These are particles with integer spin. And with particles that have integer spin, so, of course, examples include things like helium, helium-4, say a deuteron, or maybe lithium-7, right? It's an isotope of lithium that our colleague Randy Hewlett uses in some of his experiments. So what are the rules if I have bosons? Well, if I've got a two-particle wave function and I've got a particle sitting at position 1 and a particle sitting at position 2, then this is particle 1 and this slot is particle 2, then if I swap the physical positions of the particles, what's supposed to happen? Well, I pick up the same, if these are indistinguishable, so I'll put that here, indistinguishable bosons, if I swap the two particles, the wave function doesn't change, right? Now, which is in some sense a very physically appealing situation. I mean, why should it change? You've got these two identical particles, you just swap their positions, obviously nothing should change. Except we know, of course, that a second possibility is what happens if you have indistinguishable fermions, right? Those have half-integer spin. Examples include electrons, helium-3, lithium-6, another isotope of lithium that the Hewlett group likes to play with. So what happens then? Well, then you know that the wave function does something really funky. If you swap the two particles, you get back the wave function but with a minus sign, right? So it's odd under exchange of pairs of particles. Now, what does that really tell you? It tells you the famous Pauli exclusion principle. If I try and put two identical particles, and I've suppressed spin here, right? But the idea is that you're not just swapping the positions, but you're really, you're fully swapping the quantum numbers of these particles. The wave function has to go to 0 if you try and have two fermions in the exact same state. And by state, I'm including space and spin, right? So this is the Pauli principle. Pauli exclusion principle. And you all know this, and it's the reason why the Aufbau process works when you want to talk about building up atomic orbital structure, and why everything doesn't just cascade down into the 1s orbital and all your atoms, right? It's exactly this reason. I should also point out we always cheat colloquially. We always use a lot of shorthand. We usually say, oh, I can put two particles of opposite spins in a single particle state if they're fermions. That's really shorthand for saying I can create a wave function built out of some linear combination of totally antisymmetric Slater determinants. And the net result ends up being the same in the sense of having a wave function. What we all understand fully that if I've got a wave function that describes a whole bunch of fermions, that if I swap any pair of them, I should pick up a minus sign, and that means that the fermions cannot doubly occupy individual quantum states when you talk about including spin. Okay. Now, where does all this stuff come from? It comes from something called the spin statistics theorem. It's worth noting that I have never found a really nice, clean, accessible undergraduate level treatment of the spin statistics theorem. This is an example where Feynman once said, if you can't explain something to a freshman or a sophomore, you don't really understand it yourself. And someone turned around and asked him to explain the spin statistics theorem. And he stared off into space for a little while and said, okay, I guess that means I don't really understand it. It's deeply tied in with the Lorentz invariance of quantum field theory. And I know those words don't sound like they mean much when I just use them in this offhand way, but there's something really deep going on. I'll remind you that I mentioned once earlier in class, there is a book, I'm staring at it on my shelf right now, called The Story of Spin by Tominaga, who is one of the people who got the Nobel Prize for quantum electrodynamics. And The Story of Spin has like 8 different lectures about spin, and it's really cool history of science stuff and some really good physics, and then the last chapter is on the spin statistics theorem, and I find it pretty unintelligible. So let's just take it as read that bosons behave this way and fermions behave this way. Now, what are the real consequences of this for us? So if we want to label some spatial and spin state, right? We're going to talk about some spatial and spin state by, some wave vector, say, and some spin index. That's not the Stefan Boltzmann constant. That's a spin index now. What we find is that, occupation number for those states depends critically on whether you're dealing with fermions or bosons. So now I'm putting things almost in the language that we used when we were talking about about phonons and about photons rather, and the quantum harmonic oscillator states we were using for radiation, where we talked about each spatial mode was like an individual quantum harmonic oscillator, and you could have 1, 2, 3, 4, or 0, 1, 2, 3, 4 photons in that mode, and we had that latter states. We're doing the analogous thing now for particles, all right? And the idea here is that how many particles can I stick in one of these quantum states? And what you find is, if that's our occupation number for a state with wave vector k and spin sigma, that number can be 0, 1, 2, anything for bosons, right? So there's no restrictions. I can stick any number of particles I want into some spatial and spin state, okay? If they're indistinct, this is all indistinguishable particles. For fermions, your choice is very, very limited. Either your state is empty or your state is occupied, and that's it, right? So this is the Pauli principle again. And this is going to end up giving us two very nice limiting cases that will be our quantum gases, and we'll get to them very, very shortly. Now, remember, if I go back one slide here, I said, gee, our choices were bosons and fermions. That's not strictly the limit of what you can do. For your edification, I will include something called anyons, right? What on earth is an enyon? Well, the idea here, it's a generalization of bosons and fermions. The idea here is if I swap my particles, I pick up a complex phase in my wave function. So clearly we're in the limit where if alpha here is 0, you have bosons, or if it's 2 pi, you have bosons. If alpha is pi, you have fermions, and then you can make alpha some other random value, and you will not have bosons or fermions. You will have things that behave like anyons. In general, this is not possible for, as far as we know, for single elementary particles. Okay. That being said, in many body systems, especially in 2 dimensions, you can get this. You can get things that behave like anyons. If you swap, and it has deeply to do with topology. You can have weird topological things going on where you pick up phases when you swap particles. There is no, so an example of a system that behaves like this is something called the fractional, and if you want to look it up, you can, the fractional quantum Hall effect. And I encourage you to read about this if you're interested. Now, there is no general treatment of quantum gases for anyons. Right, so the statistical mechanics I'm about to show you People have not gone and done some comprehensive general version of it for anyons because it's very, very challenging. If you figure this out, you can go and win yourself a Nobel Prize. So what we're going to do with the quantum gases is instead of looking at a single particle and asking what states can or can't it occupy, to deal with our restrictions, it's easier to look at a state and ask how many particles can be in there, right? That's why we just wrote down this occupation number business. That tells us that maybe the easiest way to think about this is in the grand canonical formalism. Instead of the canonical ensemble, we're going to use the grand canonical ensemble, right? So that means that the probability of microstate of our system is going to be proportional. The probability of the system being in a particular microstate is going to be proportional to e to the minus beta. The energy of that microstate, I'll define this in a second, and then minus the number of particles in that microstate times the chemical potential, right? So if we look at the, so this is the energy that has n particles in that microstate, and then we've got minus n and the chemical potential up here. So suppose we have a single particle state that we're going to label by K, all right? I'm going to suppress the spin index now. I mean, you can imagine that I've got a sigma attached to everything I do here. I just want to minimize the clutter a little bit. So that single particle state has wave vector k. It has energy E sub k. Of that single particle state. So if I stuck one particle in there, it would have an energy E sub k, right? So how should I think about doing statistical mechanics in this situation? Well, we're going to go and use our big ol' script z, right, for state k, right, our partition function for just that, our grand canonical partition function for just that state. What's that going to look like? Well, so the point is we've got this single particle state, and it can be in thermal equilibrium with some bath at some fixed temperature T. That's what's going to define our beta, right? And at the same time, it's able to exchange particles with the bath, and that's going to help define our chemical potential. So the idea is that our system for the moment is just a single particle state labeled by K, and it can exchange energy with a bath, and it can exchange particles with a bath, right? So the partition function for something like that, the grand partition function, is going to be, we're going to sum over all possible occupations of that state, and then we've got e to the minus beta. We can pull the n of k out here. We've got n, if we've got nk particles in that state, then the energy is going to be nk times the energy of that individual state, right? So that explains why we can pull the nk out here. And then we're just going to have the chemical potential as well, right? So if I have nk particles in that state, the energy of that state, the energy of those particles is going to add up to nk times epsilon sub k, and then the chemical potential out here is going to play in like this. All right? So the sum is over possible nks, right? So for fermions, this is really easy because our sum contains only two terms. Nk can be 0 or 1. So if it's 0, then this exponential just becomes the number 1. So the grand partition function for fermions is going to look, for this particular single particle state, is going to look like 1 plus e to the minus beta e sub k minus mu. That's it. All right? Cool. So we can do a few different things. So the analog of the Helmholtz free energy here is going to be the Landau free energy. So I can write the Landau free energy lambda is going to be minus k Boltzmann T natural log my big script z for this single particle state, right? what's that going to look like? Well, it's easy to write. It's just minus kT natural log 1 plus e to the minus beta energy minus chemical potential. There you go. This is all for fermions. Okay. If we do that, then we can find the average occupancy. We can find the average occupancy by, again, if you look back up at our definition, we'd want to pull down an n sub k somehow, right? Because our actual average occupancy is going to be the sum of n sub k e to the minus beta blah, 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 all over script z. So what we're going to find is that this ends up being minus d Landau free energy with respect to mu, right? And what's being kept constant here is basically the temperature and implicitly the volume, because the volume goes into what the energy levels are. All right, for those of you who are playing the home game and you're worrying about what we're keeping constant when we take our partial derivative. So what's this actually look like? Well, I've got an expression for lambda. I can go and take my derivative, and this is going to look like e to the minus beta in the numerator, e sub k minus mu, and then in the denominator, I'm going to have 1 plus e to the minus beta e sub k minus mu. And I can divide the numerator and the denominator by this e to the minus beta term, and I get 1 over e to the beta e sub k minus mu, all plus 1. Okay? Now, let me rewrite that for 1 second here. So that is the Fermi-Dirac distribution. So what do I mean that that's the Fermi-Dirac distribution? Remember what we're doing here. We're saying I'm considering a single particle state, and I'm saying what that individual single particle state is somehow able to exchange energy and particles with a bath. What's the at a given temperature and chemical potential, how many particles are in that state? And the answer is this. Notice, by the way, that this is always, you've got the numerator is 1, the denominator is 1 plus a positive thing. So this thing is always less than or equal to 1, right? You can never have more than one particle in the single particle state. Again, remember that if it makes you feel better to picture a sigma here and a sigma here, you can do that. I'm keeping track of spin as well. Okay? So that's the Fermi-Dirac distribution. So what's the difference if we have bosons? And again, this is going to start looking very familiar to you, right? The Bose case, same deal, big script Z. Now we're going to sum over n sub k, but we're going to let that sum go from 0 to infinity, because I can have any number of bosons I want in my single particle state. And I've got e to the minus beta, and again, the n sub k gets pulled out, and I've got the energy of the individual single particle state. That's how much energy you'd have if you stuck one particle in there, minus mu. Okay, and voila, once again, we have a geometric series, which you totally know how to do. And so this is clearly 1 over 1 minus e to the minus beta e sub k minus mu, right? That's the grand partition function, right? Now, you can stare at that, and you can worry about convergence, because geometric series, you can only write them this way if the sum actually converges, which means you need the argument of this. You need this exponential thing, e to the whatever, to be less than 1, right? So this only works, that beta is positive. So, this converges, let me just write it explicitly, if beta n sub k e sub k minus mu is greater than 0, right? And you know that the particle number is not greater than or equal to, just greater than 0. The particle number is clearly positive. The temperature is clearly positive. So what that means is that e sub k minus mu must be greater than 0 for all e sub k, all right? for any E sub k, regardless of sort of how we're defining the energy. That has to be true, right? So what this implies is that for bosons, the only way you're completely safe is if mu is less than 0, right? The chemical potential has to be negative because I could make my energy nothing, and that the only way I'm going to guarantee everything still works and under those circumstances that this whole quantity ends up being positive is by making mu less than 0. All right? So let's continue onward here. The grand partition function, we had the grand partition function, the Landau free energy, for that individual state is going to be minus kT natural log big ol' script z for that state, right? And it's going to look like kT natural log 1 minus e to the minus beta e sub k minus mu. Just to remind you, we're doing bosons now. Okay. All right, so we have our same formalism as before. We can say, gee, what's the average occupation number for our bosons? That's going to be minus the partial of my grand partition function with respect to mu, again at constant t and volume. What's that going to look like? If I take a derivative, I can easily do this. I'm going to end up with e to the minus beta e sub k minus mu over 1 minus e to the minus beta e sub k minus mu, right? And again, I can rewrite that. I can say nk, the average occupation number is actually going to be 1 over e to the plus beta e sub k minus mu minus 1, okay? So that is the Bose-Einstein distribution. The interesting historical note here is that Bose actually worked this all out, and Bose knew that he was not well known, and he knew that being not well known and being from India, he was probably going to have a tough time getting this published. So he sent it to Einstein and said, basically, can you do me a favor and help, if you think this is right, and I think it's right, can you get this into the literature? And Einstein did that and was a big backer of Bose, actually. So it's kind of a reasonably nice story about politeness among scientists. Einstein did have some additional insights as well, but Bose really was the big driver on all of this. So what this means is we can, if we want, we can rewrite everything, our distribution functions in a very compact way. So the average occupation of our single particle state that we're considering here, it's going to be 1 over e to the plus beta e sub k minus mu, and then it's going to be plus or minus 1, where the plus is for the fermion case, and the minus is for the boson case. Okay. Well, now that we have our distribution functions, our Fermi-Dirac distribution function and our Bose distribution function, what can we do with this? What you know is that if I've got a whole bunch of single particle states, and they're really independent, then the average total number of particles for a given temperature, volume, and particle number, I could write the big honking 1 over n factorial grand partition function of one of these things to the n, right? But that's actually not the smart, and differentiate from there, but that's not the smart way to do that. If what we're doing is we're keeping track of states, and we're counting states, and we're figuring out how many particles are in each state on average, then what I can really do is I can just do this. I can sum over all the states, and I know how many particles on average are in each state, because I know my distribution function. So I can basically say, gee, that's the sum over all k's. 1 over e to the beta e sub k minus mu plus minus 1, and again, plus equals Fermi-Dirac minus equals Bose-Einstein. All right, even better. So that's my total number of particles. Remember, I've got each state, and it can talk to a bath that can exchange energy and particles with it. And so that means my total system number of particles is maybe has a well-defined average, but you can imagine it varying from moment to moment as particles diffuse in and out of the bath and into my particular individual single particle states. Now, so that's the total number of particles. By the way, in all of this, I'm assuming that the states are truly non-interacting, that they're not talking to each other. If they were talking to each other, I couldn't treat each one of these things independently, right? Because the energy of one state might depend on whether another state is occupied, and so on and so forth. So we're assuming non-interacting particles in all of this. Now, my energy, my average total energy for my system, is something very similar. I know the energy of each single particle state, and I know on average how many particles are in there. So I can just find, if I sum over the k's and I sum over my distribution functions, I can find the total energy. That's pretty cool. Right. So let me see here. All right. So let us actually go ahead and do, I've been thinking about this. Let's actually go ahead and do the whole, that's a terrible script Z. That's not even much better. Let's go ahead and do the full grand partition function. So I'm going to take a product over all of my single particle states. I cannot write today. So the idea here is that I've got my partition function for each single particle state. The single particle states themselves are distinguishable, so I don't need an n factorial or anything. I can just say, okay, here's my grand partition function that's a product of the partition functions of each of those single particle states. And what's that going to end up looking like? If I actually wrote them all out, it would actually end up being a sum over all the k's and all the occupation numbers of each k, e to the minus beta, the energy of each state, n sub k, just like we had before, and then we've got the n sub k here and the chemical potential. Okay, so that would be our full, goodness gracious, grand partition function, which means our full Landau potential for the whole system is going to be minus kT log of that. Right? And that's going to be minus K Boltzmann T sum over the K's of, this is sort of our, we're converting our product into our sum here, sum over the K's log of the individual z sub k's, and so that's going to end up looking like, this should be clear, that's going to be a function of temperature, volume, and the chemical potential. That's going to look like minus plus K Boltzmann T sum over the k's natural log 1 plus minus e to the minus beta energy of the state minus mu. And again, we have the plus sign is for fermions, the minus sign is for bosons. All right. One other thing to point out, in the classical limit, what do I mean by the classical limit? Well, the classical limit is one where our distribution functions are very sparse, right? Things are not very occupied. That corresponds to e to the beta epsilon k minus mu is large, so that our average occupation numbers are small. So in that limit, then the Fermi-Dirac and the Bose-Einstein distributions both approach, yes, you guessed it, e to the minus beta e sub k minus mu. So that's just our Boltzmann factor. So you will end up recovering Maxwell-Boltzmann statistics if you try and do one of these things and one of these approaches with quantum gases, and then just take the temperature to be something extremely high. Or sorry, take the make the gas extremely dilute is perhaps what I really should say. All right. So the original comment, though, where basically I said that I'm going to remove the overline now. It's going to be my sum over all the states, the occupation of each state, right? And then our energy is going to be the sum. Sorry, my app behaved a little strangely there. my sum over all my single particle states, the average occupation of each state times the energy of that state. This is a clue that, once again, we are going to do counting. We are going to somehow count states in k-space or momentum space or energy. There's different ways you can think about it, right? So, we can think about the particle in a box, and we've done this derivation a couple of different times now. I'm going to do it very slightly differently than what we've done before. So for the classical gas, our classical result was that the integral, we were integrating over all of space and over all of momentum space, right? And then we stuck a 1 over h cubed to make life a little bit simpler. And we basically did the volume integral, and we had a volume outside, and then we were somehow integrating over volume in momentum space, and we basically had the h cubed out here too. And we said, okay, we now have to integrate over the volume in momentum space, and if everything's isotropic, what we were doing in 3D was we were saying, okay, we could take 4 pi p squared dp, right? That's one approach we got. And when we were doing basically the ideal gas derivation for the classical ideal gas. Now, something I do want to point out, we could have said that we could have changed variables here if we wanted to. We could have said that the energy is p squared over 2m. If I've got a state with some momentum p, my energy is p squared over 2m. So then we can just do a variable change, right? So we find in this case that the momentum p is the square root of twice the mass of the particles times the energy. And then if I take my derivatives, that means that dp is going to be a half square root of 2m over epsilon d epsilon, right? And so I can actually just change variables. And what I would say is that, in some sense, my density of states is a function of energy, right? If I'm going to basically, if I thought of this here as my density of states as a function of momentum, my density of states as a function of energy is going to end up looking like we're going to have the volume out here, the h cubed out here. We're going to have the half, and we're going to have the 4 pi we're keeping, right? And then we're going to have, we're worried about basically the integrand. So the p squared is going to end up giving me 2m, the energy, and then the dp is going to give me the square root of 2m over the energy, and we already had the 1/2 out front, and then we have the dE. So my density of states, if I combine all of this stuff, is going to look like v over h cubed. There's a 2 pi here, and then there's a 2m to the 3/2 energy to the 1/2 d energy. All right, so this is a way of counting by energies. And if I want to actually be more careful and I want to worry about the spins, right? So if, and again, I'm sorry for the notation, but if ns equals the number of spin states, which could be, for example, for electrons, it would be 2, because I can have spin up and spin down. Then we would have the full density of states here for n as a function of energy would end up with an ns out front. And I'm going to convert my h into an h bar just for niceness. And I'm going to have the ns times the volume. And if I do this, I'm going to have 1 over 4 pi squared down here, h bar cubed. So that's all I've done with the 2 pi's and the h's here. I'm going to end up with a 2m to the 3/2 epsilon to the 1/2 d epsilon. Okay, so that's my density of states as a function of energy, right? I should point out that we could have gotten this exact same result if we'd done everything in k space, and then we had basically said that h bar squared k squared, if we said this, we would have gotten this exact same result if we started from k and wrote it in terms of energies, right? Okay, same result. So what this means is that we can use this kind of three-dimensional density of states here to do all kinds of stuff. right? So let's actually try and do that. One thing you can do is you could write down the. Now let me go back a second here, right? We said we had the full-on Landau potential involved summing over the states and worrying about the energy of each state and the chemical potential like that, right? So we can write our full Landau potential. Sorry, no K there. Excuse me. As a function of T, V, and mu, right? And we remember we had our minus plus, and then we had our KT out front. That's fine. But now we want to count up the states. So instead of writing it as a sum over the Ks, if I want, I could write it as an integral over the energy and throw in my density of states here, right? So I'm counting up all my states within a given energy range. And then I would write in log of 1 plus or minus e to the minus beta e minus mu. Whoops, wrong button. All right. And so what we're doing is we're summing over all the single particle states. We're just counting by energy this time. So if you actually go and write this, if you plug in the numbers, what are you going to end up with? You're going to end up with minus plus K Boltzmann T, number of spin states that we're worried about, volume over 4, pi squared h bar cubed. We have our 2m all to the 3 halves here. And what are we going to have inside the integral? We're going to have the stuff that depends on the energy. So we're going to have this integral from 0 to infinity, epsilon to the 1/2, natural log 1 plus minus e to the minus beta energy minus mu, d epsilon. There, I'll write it down there. Okay. If you want, you can actually do this integral. All right. What is it? Well, rather, you can integrate by parts and make it look a little prettier. You can get rid of the natural log. So if you do that, if you integrate by parts, just to get rid of the natural log, you would end up with minus 2/3 number of spin states, volume over 4 pi squared h bar cubed, 2m all to the 3 halves, integral 0 to infinity. And now that I've integrated by parts, I'm going to have epsilon to the 3 halves d epsilon up top, and I'm going to have e to the beta epsilon minus mu plus minus 1 down below, right? And remember, plus sign is for Fermi-Dirac. I'll just write it down here. Plus equals Fermi-Dirac, minus equals Bose-Einstein. Okay? So that's our full Landau potential, which means we can find anything we want from that. We could do even a little bit better. We could write down the energy, right? We could do this a little bit more simply. We could say the energy is we're just gonna count up the states. It's gonna be the energy of each state, the average number of the occupation number, basically. This is our distribution function. We're going to talk about what the occupation number is of each one of those states. And we're going to have the density of states, dE. That's it. We're just going to count them up by energy, right? And if we do that, what's it look like? It ends up having, if we plug everything in, we're going to have number of spin states here, volume over our same 4 pi squared h bar cubed, 2m to the 3 halves, integral 0 to infinity, and now again we pick up the factor of energy, so we're actually going to have energy to the 3 halves dE, and guess what? We're going to have our distribution function in here, where again the plus or minus depends on whether you've got Fermi-Dirac or Bose-Einstein. So this is it. This is our formula for the energy of one of our quantum gases. All right. And I just wanted to write down 2 more things, and then we will be done, and we will move on from there next time. So we did the energy. We can worry about the total number of particles. Same kind of deal. We're going to integrate from 0 to infinity. We're going to count up all the energies, right? And we're going to have the number of particles. So that's our distribution function again. And that's the number. That's how likely a given state at a given energy is to be occupied. and we're going to have the density of states. That's it, right? What's that look like? Well, that looks like number of spins. I'm just doing this to be for completeness here. We got the 4 pi squared h bar cubed out front. We got our 2m to the 3/2. That's a 3/2 up there. And then we've got integral 0 to infinity of energy to the 1/2 d energy, and then our distribution function, e to the plus beta, e minus mu plus minus 1 down there. That's it. And if we wanted to, we could actually do a little bit of thermodynamics for our very last thing. It turns out that from thermo, that lambda, the actual Landau potential, what does it actually equal? Well, you can do some thermodynamics, and you find out that formally it actually equals minus p times v. That comes out of our old Legendre transform stuff when we were doing different thermodynamic potentials. So what you find is that, gee, if I know lambda, I can find the pressure. All I have to do is take the minus sign and divide by the volume. So that means the pressure of one of our fine quantum gases as a function of temperature, volume, and particle number is just going to be 2/3 number of spin states, 1 over 4 pi squared h bar cubed out here, 2m to the 3/2, and then we just have integral 0 to infinity, energy to the 3/2 d energy over e to the beta energy minus mu minus, or plus minus 1, I should say. Cool. So now, with our use of distribution functions, right, if we can label our states, we can do it with wave vector, we can do it with energy. I've written them with energy here just because it's kind of simple to do. We can count up the number of particles, we can count up the total energy, we can find the pressure. In some sense, we know a lot of interesting things. Now, we're going to spend time next time examining the consequences of all of this, right? So what we're going to do is we're going to basically decide to go with the bosons and play with the bosons. Actually, the first ones we're going to do the fermions. We're going to do the fermions first and worry about Fermi gases and learn about them. And then we're going to do bosons. And so we're basically just picking which sign we want in our distribution function, and we're going to go from there. And we'll see all kinds of interesting stuff falls out. One last thing before I finish. You notice that back here, one of the things I did was I very explicitly used a very classical expression for the kinetic energy, right? I didn't worry about relativity or anything. So the fact is you can do this exact same derivation, and of course I did that, and then I went and blithely took integrals of energy up to infinity. So that's, probably a little unfair, right, that I did that. It turns out that if you want to, you can actually do the relativistic version of this problem. So you could totally write that the energy is the square root of m squared c to the 4 plus p squared c squared, right, all under the square root. You could do the whole special relativity thing for the energy, and you could still do these problems. And there are times when that really matters. So what people find, for example, is in Fermi gases, in a metal like gold or copper, the speed, the kinetic energy, I should say. Let me go back. The speed of the highest occupied single particle states corresponds to a particle with a speed that's around 1% of the speed of light. So for things like gold and copper, you can get away with not being very relativistic. But if you want to worry about a neutron star, like we heard about at the beginning of the week with the colliding neutron stars, the neutrons in the neutron star are in fact the degenerate Fermi gas. And in that case, the effective speed, if you will, of the highest occupied single particle state is a good fraction of the speed of light. So that means that if you want to do the Fermi gas that's really directly applicable to neutron stars, you have to do the relativistic version of everything I just showed you. But the point is, it's very straightforward. It just ends up affecting exactly what this term looks like. Okay? So why don't we stop there, and I will see you all on Thursday.